Okay, so this is the Kaggle script that is written in Python that we will be converting to R. This is for the Microsoft Malware detection competition, and in this competition it is a binary classification problem where the target variable is whether or not the machine in question has malware detected on that machine. There's about 82 features that we are given to try and predict whether or not machines have malware. And this script here was written by Fabian Daniel, so shout out to Fabian there. Version 28 of this script as well, just in case they come back and make some changes and you want to follow along with the same script that I'm using. And this script scored 0.677. This is area under the curve, because like I said, it's a binary classification problem. So let's get started. Alright, so these are the high-level steps or sections to this script that I wrote here in R, and this is going to be taking us through pretty much exactly what Fabian did in their script in Python. So first we'll do some setup, loading libraries and data, and then we will identify some different feature types. Those will include numeric, categorical, and then Fabian's also identifying binary features as well, just to do some special processing to those. And then we will go into some additional feature pre-processing for categorical variables specifically. That will include label encoding as well as frequency encoding for really high cardinality categorical variables. Then we will handle some missing values in those categorical features. It turns out that in this competition, test is quite a bit different than the training set we're given, so we'll have to handle that in a specific way. And then we'll get into modeling and then preparing ourselves to output the predictions to turn into Kaggle. Okay, so one thing to specify before we get started is that these comments here that say cell and then a number, these correspond to the cell numbers in the actual script here. So that's cell 1, this is code cell 2, just so you can follow along with what I'm doing in the R script and make sure you can link that back to the original. So these are some of the libraries we'll be using along with descriptions for what role they play in this script. Load in all of our data here. I like to call my train data dev. I got that from Andrew Ng, I think. And I also prefer to work with data frames as opposed to data tables, but I am using the data table disk IO functions here, so I'm reading it in as a data table just because this function is way faster than the built-in read CSV function. But because I prefer to work with data frames, I have to use this to convert it to a data frame. And I'm also taking a random sample of 4 million records from train. And I picked this number just because that was the number that was in the original script. We're also setting aside the names of the identifier, the unique row identifier, as well as the name of the target variable in the data set as well. Okay, so now we'll go ahead and identify some different types of features in our data set. So these were kind of hand-fed to us in the original script. These are the actually numeric columns that we can just kind of leave alone. So right here, what we're doing is we're just really making sure that anytime we are setting aside some features, we don't allow the ID or the target variable to be in that that vector of feature names. So you'll see this pattern quite a bit. So here in the original script, they were using list comprehension in Python to identify binary variables. And the closest thing we have to list comprehension in R is the apply family functions. So we're using the sapply function here, which is going to return a vector. So what we pass into sapply is the original data frame, along with a function, which in this case is an actual function definition, so it's an anonymous function. And how you can think of this is x is going to represent basically every column within dev. So it will take the place of every column in dev one at a time. It's basically kind of looping through all the columns. And for each column, it's going to remove any NA values it's going to take the unique values of what's left over after NAs are removed, and it will take the length of that, and we'll be comparing that to 2, and if it's equal to 2, this will return true, and if not, it will return false. So we'll go ahead and see what that looks like. It might take a little while to process there. But when that returns, it's going to give us a vector of true-false values. Here they are right here. And we are going to subset the names of our data set with that vector. And as we did before, we're going to make sure that the ID and the target variable are not within those names of features, just to be sure. So let's look at what those binary variables are. You'll notice a lot of them have the word is inside of them, which kind of makes intuitive sense here. It either is or it isn't flights disabled, or it is or it isn't secure boot enabled. So that fits the pattern of a binary variable. It's either yes or no. And now that we've identified the numeric columns and the binary columns, it's pretty easy to find the just generically categorical columns. What we'll do is a set diff, and just to give an explanation for what set diff is doing is it's taking this first vector here, which is every single name of every column in the original training data set. So anything, it's going to return anything in this vector that doesn't fall inside of this vector. And so you can see we're combining this into one vector. So we're combining the binary variable names, the numeric variable names, and then this is our ID and our train. So anything in the data set that isn't in any of these values here will be returned, which is going to be all of our categorical columns. This is a little bit redundant since we kind of just did that up here, but just to be consistent, we'll make sure that our ID and our target variables are not in those categorical feature vectors. Okay, so one other thing you might notice in the original script is this analysis on cardinality here. So what cardinality is, it really only pertains to categorical features, and it is the number of unique values inside of each of those categorical variables. So this is just a wrapper function that's going to help us with some of this logic here. Let me run this and just show you what this will give us. This is going to give us the number of unique values for each categorical column in the data set. So you can see some of these have quite a few values. This is going to cause a lot of problems. So if you were to one-hot encode this, if every single value had its own column in the data set, you would have a very, very, very sparse data set. You'd have 121,000 rows, over 121,000, columns. So that's not really how you want to go about pre-processing these categories. So we'll have to figure out something to do with these really high cardinality features here. Essentially what we're doing here, this is another sapply. So we're passing in the original data set, the training data set. This is our anonymous function, and what it's doing is, think of it once again for each column, so X is the column, one at a time. It's going to return the unique values in that column, and then it's going to calculate the length of that vector of unique columns. And that's going to give us a vector. So this is another pattern you'll see a lot in dplyr and the tidyverse. What it basically says is the output of this function is going to be passed into the first parameter of this function. And likewise for all of these subsequent lines here. So we're taking that vector of unique counts of values for each column, converting it to a data frame. This is our rename wrapper, so we're just renaming the name that's in that data frame to be just unique values. This mutate is going to just make sure that the row names, which are calculated up here, are going to come across as the actual features. And this arrange is basically like a order by, and then we wrap it in a descending because we want the higher values to be at the top. And this is what we calculated up above. So that's what we want to be descending. And then we want to filter for only the categorical columns, because cardinality is really only interesting for categorical variables. And it wouldn't really be interesting for binary variables because those are all going to have a cardinality of 2. And we don't really want to calculate cardinality for numeric variables because those are continuous and not discrete. So that's just an explanation of what's going on there. And then you'll see me execute GC every once in a while. This is garbage collection. So some of these data sets are pretty big, so we just want to make sure that we are using our memory efficiently and returning things to memory, freeing up memory pretty much any chance that we get. Okay, so we just looked at the cardinality of some of these categorical variables, and now let's talk about how we might go about pre-processing some of those very high cardinality features. So this function is going to basically create a mapping table for each value within a given variable. It is going to tally up how many times that value shows up and create a little mapping table that we can then join into the original data. And the new value will then have the column name will have this prefix so that we can quickly identify which of these new columns have been frequency encoded and which have not. So these are the kind of troublemaker features that we need to use frequency encoding for instead of any other pre-processing method. So these are the high cardinality features that we want to pre-process. So here we're going to use lapply to just ensure that these features are currently represented as character, the character data type, which is basically like a string in R. So I'm going to go ahead and run this. It's very similar to sapply, but instead of returning a vector, it's going to return a list. And a data frame under the hood is really just a collection of lists. So this allows us to say, okay, for these columns in this data frame, execute this function and then put it back into these columns in this data frame. So it's really just a one-to-one mapping there. So just to get a feel for kind of what's going on here, let's take one of these names and let's run a table function on that. Just to kind of see what's going to happen whenever we do this feature encoding here. So these are all the values. It's kind of confusing because the values of this category themselves are numbers, but this is a category, this is a category. So we can just pretend like they're strings really, and it won't make much of a difference. But for what we're doing here, frequency encoding, basically what we're going to take is if this is the value we're looking at, we're going to use 7 as the new value for that feature instead of this value here. So we're just replacing the actual category value with how many times that category shows up in the data itself. And just to get a better view for what that might look like, I'm going to manually set our index value to 1 for this loop here. And in this loop, we're going to be applying this frequency encoding calculation, function that we defined up there. So let's just step through this kind of step by step. So this is just identifying which feature we're looking at any given time. So right now, this variable is this first one in the vector we defined up there. And here we will actually be running that function we defined to calculate the sort of mapping table. So let's get a look at that. So this is what we'll be using to map this new feature given this old feature here. So this is where we'll be joining that data into the original data frame. And then because we don't want both this feature, the original feature, and this new feature in the data set, we're going to be removing the original column. So we'll be removing this one and then keeping this one. So we'll go ahead and let that entire for loop execute. Okay, so our for loop is complete. It has executed all of the frequency encoding. One thing I forgot to mention though is you'll notice I'm actually setting these to data tables. And the reason I'm doing that here, I wrote a comment about this, but it's because joining data tables is much more efficient in terms of both memory and just how fast it is, as opposed to joining data frames. So I'm converting them to data tables, executing these merges, basically joins, and then converting back to data frame just because, like I said, that's what I prefer to work with. So that's important to note as well. And so this categorical columns feature, or vector here, this is representing the categorical columns that we kind of still have to figure out a way to pre-process. So what we're going to do is we're going to make sure that these frequency encoded variables don't show up in that categorical column. So we're going to go ahead and execute that, and then go ahead and garbage collect just to make sure we're freeing up as much memory as possible. Okay, and once again, I guess this is a little bit redundant, just following the original script, but I want to make sure that these once again are represented as character. So just being extremely explicit about the data types there. So now we'll start talking about how to pre-process some of the remaining categorical features. And for that, we will use label encoding. And just to give a quick idea for what that might look like. So say you have a categorical feature here, and we'll just go with really basic animals here. Let's do one more. Okay. So if this is our feature of categoricals, if we were to label encode this, then one method for doing that in R, it's actually pretty easy. We'll do it as integer, as vector, and then we'll do our feature there. So basically it's just, first it's sorting these character values, and then it is converting them to an integer type. So in this case, cat will be 1, dog will be 2, fish will be 3. So you can see for each of those values, it's just mapping it to the integer value that now represents that feature. So you can kind of think of it as converting your categories into what appears to be an ordinal value, but in this case it's not technically ordinal, it's still nominal. I think light GBM has a way of handling that, so we will eventually tell light GBM which features are categorical and which are not, just so it knows how to handle the categories in its own kind of special way. So in the same way that we handled the feature or the frequency encoding, this is going to create kind of a mapping table as well. And then this is our loop for executing the same type of logic, just with this function instead of the frequency encoding function. And this time there's quite a few more of these categories that we'd like to execute label encoding for. So I'm going to let this run, and then we will come back and see what that looks like. All right, so that took a little while, but we have finally completed that loop. And at this point, we're pretty much done with the majority of our pre-processing. So what I like to do at this point is I like to take a snapshot of the entire environment, everything that's loaded into memory. And you can do that with save.image. And this will create a .r data file. And this is a binary file format that is specific to R, and you can read and write these pretty quickly. So at this point, you wouldn't have to, if I were to delete everything in this environment right now, given that I've saved this already, I can then load the entire environment at once, and I can pick up kind of where I left off. So this is just kind of a heads up for if you're following along. It might be a good idea to just save a checkpoint so you don't have to wait for this whole script to pre-process again if your computer were to crash or if something were to go wrong. So now we'll move on and talk about handling missing values. So one thing I mentioned a little bit earlier is that the test set in this competition looks quite a bit different than the training set. And this caused there to be a lot of missing values, specifically for this type of merge right here. And so I had to look up the way that Pandas was handling missing values in the original script, because I want this script I'm writing to be as close to the original as possible. And this is what I found. So in the original script, they are using getIndexer to do their label encoding. And what that's doing is, say there's a value in your current list that you're trying to map to that does not exist in your index, it will actually return a -1. So that is the behavior that I am mimicking here. So that is our replace value. I have some other ideas for what I want to do whenever I come back and iterate on this script, but for now we're going to keep it as close as possible to the original. So I'll go ahead and kick off this for loop. And what this is doing is it's going through every single column in the data set, and if that column is one of the target or ID columns, then it will go to the next iteration, and then it will also identify, is this one of the columns that has been label encoded. So I guess technically that's a little bit redundant, because if this is true, then that can't be true, but oh well, we'll just move on. So if the value is NA in one of these label encoded columns, then we are going to replace it with the replace value. So sorry, this is actually that separate thread I was talking about for what I want to come back and try, but this will never resolve to true here, so we'll just jump down to this statement here. So we will replace missing values, which are currently NA, and we will replace those with -1, so that we are pre-processing the exact same way as the original script in Python. And now we are finally ready to actually get started with modeling. So before that, we'll go ahead and set aside our target variable. It's a little bit confusing, but at first this variable was just the character representation of the name of the target variable, but now this value, or this variable, will hold the actual values of our target. So as we mentioned before, binary classification problem. So a 0 represents a machine that does not have malware, and a 1 represents a machine that does have malware. So as you can see just from this really small sample, it is a pretty balanced data set in terms of the target variable. So this should be pretty interesting. And then we'll go ahead and remove the target variable from the data frame, just because we do have it already set aside here. These are the original parameters that were in the Python script, and all I really had to do here was just wrap them in a list, just because that's an easier way to pass all the parameters into the model once we start modeling. So now what we're doing here is creating our folds. So I will set a random seed, just so this is reproducible in case you're following along. And we'll set up the number of folds, and then we will create a uniformly distributed number of 1s, 2s, 3s, 4s, and 5s to represent every single one of our folds. So here's a sample of what that looks like. They are uniformly distributed, but they won't be exactly equal. Like there might be a few more 5s or a few more 2s or something like that, but it's pretty close. We can actually show that real quick if we want to. We can do a histogram. Oops. So yeah, that's about as close to uniform as possible, with still being random. And so here we're going to actually boil that down to indices. So now what we have are the actual indices. Let's go ahead and limit that to just the first few. And then let's see what some of the other folds look like as well. So that was fold 1, here's fold 2, 3, 4, and why not? Let's just do 5 as well. So one thing you'll notice is they are mutually exclusive, so there is no overlap between the different folds, which is generally what you want whenever you're trying to do cross-validation, unless you you're allowing replacement with your sampling if you're trying to do some sort of bootstrapping. But for now, we have plenty of data, and it's very balanced, so we're just going to leave it as a normal cross-validation, especially since that's what's being done in the original script. So we've done this a few times now, but just really trying to make sure that this categorical columns, which is the vector of column names that are categorical columns in the data, just want to make sure that those do not include our unique identifier here. So we'll just make sure that that's not in there, and we will do the same for features. So now features is going to represent every single row in the data frame currently, the train or dev data frame that does not equal the unique identifier column name. So you can see we have some of our frequency encoded features in here, as well as our label encoded features. And we don't have to worry about the target because we already removed that up here. So now the only non-feature value or non-feature column in the data set is the unique identifier. Okay, so now we're going to pre-allocate some vector space for predictions and some of our scores as well. So OOF stands for out of fold. So we have 5 folds, and each of those 5 folds is going to take turns being the validation set, while the remaining 4 folds are going to be used for training a classifier. So this is going to be the collection of all of those predictions that we accumulate through looping through each of those folds. And then this predictions vector here is going to be the test predictions that will actually be passed to Kaggle to evaluate how we're doing on the public leaderboard. And then this is a very small vector, so we probably didn't need to pre-allocate it, but just 5 zeros in this vector, and we'll replace these with the actual scores for each fold as we iterate through them. So here's our loop where we will be doing just that, iterating through, and then as we get done with the first fold, the first iteration through the for loop, we will replace that with the first area under the curve score, and then second, third, and until we have all 5. Okay, so now we are ready to dig into this for loop and see what's going on under the hood here for our cross-validation modeling. One of the easiest ways to do that is to set our iterator here manually to equal 1, and then just start walking through some of the for loop steps to see what we're doing. So first we get this message here just telling us which fold we're currently processing. Then we'll set up our train and validation indices. So what this is doing is setDiff, once again, very important function. It's telling us to return all of the indices that are in all folds where they're not found in the first fold, or the ith fold, which in this case is the first. So that's giving us the remaining 4 indices, or 4 folds worth of indices that we'll use for all of our training data. And then the validation data is a little bit easier. It's just basically equal to this. It's the things that are in the ith fold, right? Because the ith fold is what we want to use as our validation. And we'll use those indices here to subset our train and validation. Inside the for loop, I do like to call it train whenever I'm doing cross-validation. And then here, what we're doing is identifying the column indices for categorical variables. I found that on this link here. I'm not sure if you still have to do this, but in the examples using LightGBM with R, they were only using column indices to identify categorical features. So I wanted to keep that consistent with some of the examples I saw on the GitHub page for LightGBM. And then here is where we will create the LGB dataset. So a lot of these GBM or gradient boosted machine packages, just like XGBoost and LightGBM, they will have their own data representation. So you have to convert generally from a matrix. Usually you can't just pass in a data frame. So you have to convert the data to their data format before being able to train So we'll do that for train and for validation. Do some garbage collection, free up some memory. And this is where we'll actually start doing the training. So here we'll set this, this is the value that the original script had. It's just kind of an arbitrarily high number. And then here we'll pass in, these are the parameters that we set earlier. There they are in list format, just as a quick reminder. We'll pass in train data as the data parameter, and then num round as n round, which is just this value here. And then valids, so this is what we want reported out. So it's going to print out scores as it's iterating through these data sets for both train and validation. This is useful to see kind of how your validation set is tracking score-wise compared to your training data. And early stopping, so once it gets its best score, it will go 200 iterations beyond that just to see if it fell into some sort of kind of local minima and see if it can keep improving. And if it can't keep improving 200 iterations past its best iteration it's seen so far, then it will stop. And so that's kind of why we set this arbitrarily high, is because we're relying on this to be our stopping point. So if we ever were to hit this value here, we'd probably either want to increase this or maybe do something with our learning rate, maybe speed it up a little bit, but this should be fine. And I'm kind of cheating because I know this is fine because this was in the original script, so we will leave that alone. Okay, so up until this point in our for loop, we have trained a classifier on 4/5 of the training data, and then we have set aside this 1/5 of the training data as our validation. So here is where we're actually predicting on that validation set, and we're using the validation index to put those predictions into the out of fold prediction that we pre-allocated the space for up here. So as of right now, this is all just zeros, and then what we're going to do is replace those zeros given this index with the actual predictions for the validation set. Okay, so next, what I saw in the original script, which I thought was a pretty good idea and I wanted to mimic here, is this concept of identifying feature importance for each iteration of the for loop and then combining them at the end. So what we're going to do is, if it's the first iteration, we're going to generate the feature importance data frame. And if it's not the first iteration, then we're going to create a different version of the feature importance for that specific fold, and then we're going to combine it onto the original. So we could have pre-allocated this as well. We could have created this data frame ahead of time, but I like to do it this way just because I think it's cleaner to keep it inside of the loop with this little clause here. If we didn't put this clause in here, then if you think about it, it would just overwrite this data frame every single time. So this is kind of a way of making sure that we can keep track of this throughout all iterations of this loop. And then at the end, we'll be able to average across I, which in this case is the integer representing which fold we're on at any given time. So that's going to give us the ability to see feature importance within each fold and then also average that across all folds at the end. Okay, so next what we want to do is we want to actually score this validation set for this fold. So we'll use the area under the curve function from the model metrics library. And what that's going to ask us to provide is the actual values, which are the target values for this validation index for that 1/5 of the data that we're using as the validation for this fold. And we will also pass in the predictions, which we stored in our out of fold vector here. And we will use the validation index there as well to capture what we've predicted already. And we'll pass those into the AUC function to get our score, and we will put that in the fold CV scores vector that we created earlier, indexing by the fold number. So each iteration it will overwrite this value and then this value and so on. And then finally, what we're doing here is we are capturing all of our predictions on the test data set, and storing them in this value here. And what we're also doing is we are accumulating them. We are adding them on top of each other and storing them here, just because then later on what we can do is average them across all folds whenever we write out to disk our predictions that are ready for testing on the Kaggle public leaderboard. Okay, so that's enough explaining the loop, so let's go ahead and kick this off and see what that looks like. So as mentioned before, you'll get a message telling you which fold is currently being processed, and then we will start to see some messages from the model itself. So it looks like what it's doing is it's taking all of those negative values in the categorical features that, if you recall, we were replacing with -1 to be consistent with the pandas functionality. It's just converting those to not a number. So it looks like we really didn't have to do that. So I guess that's fine. It should still be very consistent with the original script. And then down here, so when I mentioned this valids parameter, and we passed that a list of both the training data and the validation data. The reason for that was so that we would get this report out here. So this is telling us what the current score is for each iteration through the model at any given time for both the train data set right here and the validation data set over here. So one thing you'll always notice is that for the most part, train should be higher than your validation set, but if it's significantly higher, then you might need to revisit some of your parameters because you're likely overfitting. So shouldn't be too big of a problem here, just because we are using all of the same parameters that the original script was using. And this will take some time, just because this is still on the first iteration, and this it'll probably get to, I'd say probably between 5 and 6, maybe 700 iterations for each of the for loops, or for each of the iterations in the loop for cross-validation. So we'll go ahead and pause there and come back once this is done. All right, so we are finally done training here. I actually let that run overnight just because it does take a little while to complete. So I did want to go over what we're doing here to actually collect these predictions. So within the loop itself, for each fold, we are generating predictions here, and we are taking the cumulative sum of those predictions and storing them in this variable right here. So then outside of the loop, we divide by the number of folds, and that will give us a nice average across each fold for the predictions for test. Then we will combine that into a data frame. So here, machine identifier, this is just the ID, the unique identifier for each machine, and we will keep that as it is in the normal data set here. And we will also have this has detections, which now is going to be the predictions from our model after we just averaged them across each fold. So now we can see what that looks like here. I think I spelled that wrong. Oh, I haven't created it yet. There we go. Okay, so now we can see for each machine identifier, we can see the prediction. So the higher this prediction is, the greater the chance our model believes that this machine has detections. And this file is ready to go. So here we will write it out to disk and submit it to Kaggle. All right, thanks for watching, and I did end up submitting this output to Kaggle just to see how close it was to the original. I think the original was 0.677, so very close as expected, about 0.002 off, so that's probably caused just by randomness with how I was subsetting the original training data. So we're not going to be breaking any records with this score here. Looks like that puts us in over 1,000th place, but it's a decent starter, so it should be a good starting point. Start making some changes to the script and see if we can start getting closer to this 0.7 range. It seems to be where the top of the leaderboard is at right now. So if you have any questions, leave a comment and I will get back to those as soon as I can.